Good evening. So today I will be again continuing with the design of combined footing, that is the beam and slab type combined footing. So as usual, so for first 1 minute I will be brushing up what are all the things that I have done in the last class. Okay, so I have taken a design problem. In that, so the first step it was the data part, the second step it was the dimensions of the combined footing. Okay, dimension means as it is a rectangular type, so it will be length into breadth into depth. So we have calculated the length, breadth was already given in the question. So we are in need of the calculation of the depth. Okay, so next what we did, we calculated the projections and we calculated the SFD and BMD. So till here we have done it in the last class. Now let me continue further. Okay, so now I will be moving on with the design part. So next heading, I think it's the fourth step, I guess. It's the design of footing slab. It's the design of footing slab. Please remember this word, design of footing slab. Okay, so to explain this, first let me write down the 3D diagram of the combined footing. So it will help us in understanding. Okay, so now I will be concentrating on this particular cross section. Okay, I will be concentrating on this particular cross section. So this will be the diagram. Okay, so now I will be showing the continuation mark. So I can't show the continuation mark because it's a beam. Okay, so now I know what is the total distance. What is the total distance? It's 1.8 meter. Okay, what is the width of the beam that we have assumed? Observe, what is the longest dimension of the column? So assume that as the width of the beam. In the last class itself I have told you people which column is having the higher dimension, assume the width of the beam of that particular dimension. Here there are two columns. Okay, one is 300 by 300 mm and one more is 400 by 400 mm. So we will assume the width of the beam as 400 mm. So please remember, I will be writing here itself, assume width of beam as 400 mm. Assume the width of the beam as 400 mm. 400 mm means 0.4 meter. Okay, so total it is 1.8 meter. So out of 1.8, if I deduct 0.4, the remaining is 1.4 meter divided by 2. So here 0.7 meter and here 0.7 meter. Any doubts in this? So total if I add all these things, it should be 1.8 meter. So now the main thing is, in the dimensions we have calculated the length and width, so we are in need of the depth. So I am in need of this depth. Please remember, so I am in need of this depth. Okay, so will you people accept that for every action there is an equal and opposite reaction from the soil? So soil will be exerting its pressure onto this footing. So upward soil pressure we have already calculated. What is the value of the upward soil pressure? It's 158.73, I guess. Yes, 158.73 kilonewton per meter square. Please remember, but as it is a UDL, okay, as it is a UDL, the unit of UDL is kilonewton per meter. I need to convert this. Okay, so I need to multiply it with some value. What is the name? So it is the footing slab. In the previous thing, while calculating the BMD and SFD, I have considered the length, total length 7 meter. Okay, there what I have done, 158.73 into, I have multiplied it with width 1.8. But here, observe here. So the soil pressure is acting in this direction. So in this direction it is the length 7 meter. But as it is a slab, I will be considering 1 meter strip. I think you people know that for slab always we will be considering 1 meter strip. Okay. So now the value is 158.73 kilonewton per meter. So this is the soil pressure that is acting on the footing. Now the important thing is, let me consider this. Observe. Let me consider this book. Okay. Let me consider this book as a footing and a column is placed like this. Okay. Whenever the column is exerting pressure onto the footing. Okay. Whenever the column is exerting pressure onto the footing, don't you think that it tries to push it? So it tries to push it. So the other parts of the footing will tries to lift, but where it exactly bends more, observe here. So whenever the column is exerting load onto the footing, so this junction, this junction is the one which is more critical. This portion, that is the face of the beam. Don't think that it is some distance from the beam. It is almost on the line of the beam. But to show the distinguish, I have written it somewhere away. Okay. So now this is the critical point where the bending moment will be maximum. So let us calculate what is the maximum bending moment. Okay. Let me take this diagram. About this section I want, instead of marking it as a fixed, let me mark it as XX. Okay. So now we have a portion of footing like this, and we have a uniformly distributed load UDL, and that value is 158.73 kilonewton per meter. Okay. So what is this distance? So we know that it's 0.7 meter. So moment about XX is nothing but equal to force into perpendicular distance. If I want to convert the UDL into point load, it is 158.73 into 0.7. To convert that into point load into 0.7 by 2, because force into perpendicular distance. So what is the value? Let me directly take it from the book. Okay. So the value that we will be getting is, so it's 38.89. It's 38.89. It's 38.89 kilonewton meter. Okay. Now as we are doing the design, I want the design moment. So it's 1.5 into 38.89 kilonewton meter. So if I multiply that, the final value that I am getting is 58.33. It's 58.33 kilonewton meter. So we have calculated the bending moment. Okay. So now this is the moment that is coming on the footing. Okay. So for this, what is the depth I need to provide? Let me calculate that. So to find the effective depth, so under the design of footing slab itself, to find effective depth, to find the effective depth, I think you people remember a formula. MU limit is equal to 0.36 XU max by D into 1 minus 0.42 XU max by D into FCK BD square. Yes or no? So now, what is the value of MU limit? Let me substitute this value, 58.33 kilonewton. I will be converting this kilonewton meter into Newton mm. So multiplied by 10 power 6 is equal to 0.36 into, so what is the grade of steel that they have given it in the question? I think it is Fe415. Yes, it's Fe415. So for Fe415 grade steel, what is the value of XU max by D from IS 456? It is 0.48 into 1 minus 0.42 into 0.48 into FCK is 25 or 20, let me check it out. So here it is 25. So here it is 25 into breadth. As it is a slab, I will be going with 1000, and as I am in need of the effective depth, so I will be writing d square as it is. So using the calculator and solve option, so what is the value of d that we get? So the value of d that we get here is 130.05, 130.05 mm. Yes or no? So now using 60 mm effective cover, using 60 mm effective cover. Okay, so overall depth is equal to 130.05 plus 60. So it is approximately 190.05. Can I make it approximately as 200 mm? Yes or no? So it's 200 mm. Now the important thing is it's a footing. Okay, it is resting on the soil. So there will be a huge rubbing action when load is getting transferred from the footing to the soil. Okay, huge rubbing action. Rubbing action is nothing but the shear. So therefore what I will be doing is, from shear consideration, please remember this is very important point, from shear consideration, double the depth. So therefore what I will be doing is, overall depth 2 times I will be taking, that is 400 mm. As we know that effective cover is 60 mm. So 400 minus 60, so it's 340 mm. So now we came to know what is the length of the footing, what is the width of the footing, and what is the depth of the footing. So now as we have calculated all these things, so what is the final thing that I need to do here? So as it is a footing slab, I need to calculate the spacing of the bars. If I want to calculate the spacing of the bars, how much spacing you will be giving? So or how much spacing we need to give? It depends on the area of steel. How much area of steel you need to give? So how much it bends. Okay, so we have already calculated how much it bends. So now let me move on with the area calculation. So now we'll move on with the area calculation. So now area of main steel, I will be going with I will be rubbing this part. So next one, under design of footing slab itself, area of main steel, that is AST. Okay, so how to calculate the AST? I think you people know the formula. mu is equal to 0.87 Fy AST into D into 1 minus Fy AST divided by FCK B into D. Yes or no? So now moment will substitute the same value. So it's, what is the value that we got for the moment? It's 58.33. So it's 58.33 into 10 power 6 to convert that into Newton mm. So 0.87 into Fy is 415, AST only we need to calculate. So D value is 340 into 1 minus Fy is 415, AST we need to calculate, divided by FCK is 25, breadth is 1000 for slab, effective depth is 340. So using the calculator, if we solve for AST, the value of AST that we get is 486.73 mm square. Okay, so I think in the previous classes I have told you people, whenever you are getting a value of AST as 300, 400 or 500 around, always do check for AST minimum. If it is 5,000, 2,000 and all, usually there is no need to check for AST minimum. But here I will be doing for AST minimum check. So check for AST minimum. Check for AST minimum. So what is the formula to calculate the area of minimum steel? So it's 0.12% of gross area. 0.12% of gross area. It's 0.12 by 100 into breadth is 1000 into overall depth is 400. So what is the value that we get for that? So it's 480 mm square. It's in a close range. 480 mm square. Observe here. So here whatever the AST due to the moment that is coming on the structure, it is 486.73. Minimum AST that we need to provide is 480. So AST that we got based on the moment is greater than AST minimum as per the code. So hence say, by chance, if the AST value was lower than this AST minimum, then you would have taken AST minimum value. So keeping this particular value, we would have continued further. Okay. So for now, it is safe, hence safe. So hence safe. So no problem with this. So now, as we have calculated the area of steel, finally what we need to calculate, it is the spacing of bars. Yes or no? If I want to calculate the spacing of bars, I need to assume the dia of the bars. Okay. So either assume 10 mm or 12 mm. Okay. So don't go beyond, or maximum of 60, not more than that. But here let me check. So what is the area of steel? Because I can easily directly take the values, that's why I am taking the same dia of the bars. Okay. Here they have assumed 12 mm dia bars. Assuming 12 mm dia bars, spacing is equal to pi by 4 into 12 square by AST. It's 486.73 into 1000. So what is the spacing that we are getting? So it's 232.3 mm. It's 232.3 mm. 232.3 mm. So this is the spacing as per the moment. Okay. Code suggests something else. So as per the code, spacing is least of the following. I think you people remember this. Spacing is least of the following. Spacing is least of the following. First one, it is 3 times the effective depth. So it's 3 times 340. So 3 zeros are 0, 3 fours are 12, 1 carry 10,020 mm or 300 mm. So out of this, this and this, which is least, will go with that. So here the least is 232.3 mm. It's 232.3 mm. So can we go with 200 or 225? Okay. So here what they have taken is, they have taken it as 225 mm. Hence provide, I will be rubbing this. Okay. Because whether I need this diagram or not, we'll see that. But for time being, I will be rubbing this. So finally what we can do is provide (12 mm) dia bars at 225 mm center to center. 225 mm center to center. So now I have calculated the area of main steel and its spacing. Now let me go with the distribution steel. Okay. So next, under the heading, the design of footing slab itself. So it is area of distribution steel. Area of distribution steel. Okay. So I think the distribution steel value you people know, it is nothing but the AST minimum value. So it's 480 mm square. Okay. So now assuming, usually go with 8 mm or 10 mm. I think here they have assumed it as, so 8 mm. Okay. Assuming 8 mm dia bars. So spacing is equal to pi by 4 into 8 square divided by 480 into the 1000 mm. So what is the value that we are getting here? So it is 104.72 mm. 104.72 mm. This is based on the code value, AST minimum. Code suggests one more thing for the spacing. So what is that? Spacing is least of the following. Spacing is least of the following. Spacing is least of the following. So what is the first one? So it is 5 times the effective depth. I think you people remember all these things. So 5 times the effective depth is 340. So zeros are 0, 5 fours are 22 carry, 5 threes are 15, 17. So it is 1700 mm. The second one is 450 mm. Okay. So out of this, this and this. So which is the least? So it's 104.72. So can I go with 100? Reduce the spacing. Reduce the spacing means you are increasing the steel. Okay. So provide 8 mm dia bars at 100 mm center to center. So we have calculated the area of main steel. So we have calculated the area of distribution steel. So now we need to do the check for shear. So now we need to do the check for shear. Observe, I will be rubbing this. So next heading, it is the check for shear. So under the design of footing slab itself, it is the check for shear. I think you people know there are 3 steps: nominal shear stress, maximum permissible stress, and the last one is the design shear strength of concrete. Okay. So the first one is nominal shear stress. But the thing is, observe, let me write down the diagram again. Okay. So now, so this value we know it, it's 0.4 meter. Okay. So there will be an UDL acting. So we have converted that. So let me write down that value itself, 73 kilonewton per meter, not millimeter square, because let me assume that I have multiplied it with 1 meter. Okay. So now please remember one thing. Okay. So shear, whenever a footing is loaded by the column, when column exerts load onto the footing, observe here, when column exerts load onto the footing, it punches. So what will happen is, where the point of contact of the column is there, that will not be subjected to rubbing action, but apart from that particular portion, try to see this, observe, whenever I am pressing this, don't you see that the other portions of the book are getting lifted up? It means that at a distance d from the face of the beam, so the shear force comes into picture. Try to observe here. So whenever I am applying the column load, okay, so the sides are getting lifted up. So from where the shear force takes in, shear force comes into picture. So at a distance d from face of the beam. So that's why what we will be writing here is, so observe here, here only I will be writing. So shear force will be maximum. Shear force will be maximum at a distance d, from the face of the beam, So please remember this. So from the face of the beam, let me draw a section. Okay, so I will be calling this as YY because already I have considered XX. So this is the section which is acting at a distance d. What is the value of d? It's 340 mm. Okay, I will be writing it as 340, so 0.34 meter. So what is the total value? It's 0.7 meter. Already we have calculated it. So then what is the remaining distance? Okay, so what is the remaining distance? So let me rub this. So this particular distance from here to here. So total 0.7 minus 0.34, it is 0.36. It's 0.36 meter. So it means that the shear force is maximum about this particular section. Because as we are doing the check for shear, the first step is the nominal shear stress. So tau V is equal to VU by BD. I want the VU value. So to calculate VU, we are doing all these things. Okay. So shear force is maximum about YY axis. So shear force. So SF about YY axis is equal to. So first let me separate this diagram and write it down. So it's YY. So there is an UDL. So it's 158.73 kilonewton per meter. This distance, it's 0.36. So I want the shear force about YY axis. So about YY axis means, observe here, force into perpendicular distance. This is an UDL. I need to convert that into point load. Point load we have converted into perpendicular distance. It is nothing but 0.36 by 2. So what is the value that we are getting? So the value that we got here, so is 57.15. 57.15 kilonewton. But we need the maximum value. Shear force at YY is nothing but V value. Okay, shear force at YY is nothing but V value. I want VU value because I want the design value. So multiply it by 1.5. So it's 1.5 into 57.15. So what is the value that we are getting? So it's 85.73 kilonewton. It's 85.73 kilonewton. It's 85.73 kilonewton. So now let me go one by one. I will be rubbing this. So I will be going with the step 1. So under check for shear, the first one is nominal shear stress. That is tau V. So tau V is equal to VU by BD. Okay, I know each and every single value, substitute it. So VU value is, so 85.73 into 10 power 3, okay, divided by breadth is 1000. So what is the depth value? It's 340. Okay, so whenever we solve this particular value we get, so it's 0.25. It's 0.25 Newton per mm square. Okay, let me go with the second one. I think you people know. It is the maximum permissible shear stress. Maximum permissible shear stress. That is tau C max. For now it is not M20 grade, for M25 grade concrete, for M25 grade concrete, okay, from table 20 page 73 of IS 456 So what is the value of tau C max? It's 3.1 Newton per mm square. If it was M20, then tau C max value, it was supposed to be 2.8 Newton per mm square. Okay, so now comparing, so this is the value as per our design. Code suggests this value. So whatever the value that we get should never exceed this. So comparing tau V, that is 0.25 Newton per mm square, with tau C max, that is 3.1 Newton per mm square. Okay, tau V is less than tau C, hence safe. Hence safe. Okay, so now let me go with the third one, that is design shear strength of concrete. Design shear strength of concrete, that is tau C. So in the previous design, that is in the design of cantilever retaining wall also, we have done all these things. So if I want to calculate the tau C value, first we need to calculate 100 AST by BD. Yes or no? So 100 into, I think it is 486 point some value, I guess. So it's 486.73 divided by breadth is 1000 and effective depth is what? So effective depth is 340. So what is the value that we are getting for this? Getting here is 0.15. It's 0.14. Okay, so the value after solving this, the value that we are getting is 0.14. Okay, so using this particular value from table 19 page 73 IS 456. Okay, so if I go with this particular value, the value of tau C that we are getting by doing the interpolation and all, so it is 0.29 Newton per mm square. 0.29 Newton per mm square. But here please remember, whenever you are doing it for the slab, okay, so whenever you are doing it for the slab, whatever the value that we are getting here, so final tau C value should be K times the tau C value. Should be K times the tau C value. Then what is this K? So it's a constant value that we need to check it in the code. Okay, again the page 73 of IS 456. So there you people can easily check out. So the value of K, it based on it is the depth of the footing. So based on that 400 mm overall depth and 340 mm effective depth, the K value we can take it as 1. I am not taking it directly, it is from the code. Page 73 code, I want you people to check it out. 72 or 73, you just check it out. So the value of K that we get over there is 1 into 0.29 Newton per mm square. Now we'll compare. So tau V, what is the value that we got for tau V? So it's 0.25. Okay, so what is the value of tau C? It's 0.29. Okay, so tau V is less than tau C. Okay, one thing is sure, as it is a slab, Okay, you will never get the shear reinforcement. As it is a slab, you people will never get the shear reinforcement. If by chance, if tau v is exceeding tau c, then what we need to do? We need to increase the thickness. Already while considering the shear consideration, we have doubled the thickness. But still, if tau v exceeds tau c means we need to increase further and do the design again. But here tau v is less than tau c, no need of providing shear reinforcement in the form of vertical stirrups. But as it is a slab, we can't provide it also. So hence say, hence safe. Okay, so this is how we need to do it. Okay, so next we can't do the check for deflection. Actually, we were supposed to do check for deflection, but here I will not be doing it. What is the reason? The reason is the footing is resting on the soil. Yes or no? So, as there is a support from the soil, so there is no need to do the check for deflection for footing. Okay, so the further things will continue it in the next class. So, for today's class, we'll wind up. Thank you.